This video is a little bit freeform, but the point of it is it's to show you by no means all possible examples, but just a few examples that are quite generic of thinking, that is, thinking with physics, with this particular physics, that the work done by the net force is the change in the kinetic energy. So I have, let's see, I've got 4 different sort of generic situations. In some cases, you'll see numbers. In some cases, you'll see vectors. I'll explicitly draw vectors. I'm not going to finish any particular problem, but I'm just going to show you examples of thinking with the work-energy theorem, what it might look like, what kinds of expressions I might write down, and drawings, and what I'm imagining happening. Yeah, so here I go. So the first example is a person lifting a barbell. So here's a picture. Here, let's see. So this is going to look kind of weird, but here is a person, and they are squatted down. So that's them. And here are their arms. And they've got the barbell. And the barbell is here. And I'm going to be very careful. I'd like you to notice that the ground that the person is standing on is not touching the barbell. So the barbell, you can see this heavy weight is actually already been lifted so that it's no longer in contact with the ground. And then this super strong person is going to use all the musculature of their body and ultimately produce some forces that are going to accelerate, that is, add motion to the barbell, right? So F net on the barbell at the beginning is going to be bigger than the barbell's weight, for example, and then sort of lift it up to some, say, mid position. So here is after the person was able to stand up, and they've got the barbell underneath their chin. So they've done the work necessary to get it here, but they're not finished. This is an Olympic lift, and they're going to lift it above their head. I think that's what Olympic lifting is. So they go ahead and they finish. So they're still standing up tall, same height. Here they are, touching the ground, and they have now the barbell above their head. Okay, so I'd like you to notice that if I was to try to imagine what kind of force is this person producing, the force on the barbell by the person is really complicated. Sometimes they're producing a force on the barbell much bigger than actually the weight of the barbell. And if they can cause that to happen, the barbell will accelerate and gain motion upwards. But as the barbell goes up to this person's shoulders and they can rest and the barbell is momentarily not moving anymore, they were able to relax the force, and the force on the barbell for a short amount of time was much smaller than the weight of the barbell. And so what this person could do is allow the barbell to come to rest just by sort of turning off their force on the barbell. But then they have to turn it back on and press it up above their head. And now, if the barbell is at rest here, so they are holding it above their head with no motion, and the barbell started its trip from rest, you notice that if I call this the initial situation and this the final situation, the kinetic energy in the final situation does not have any, it's 0 joules. And the kinetic energy, and I'm talking about the energy of the barbell, the motion energy of the barbell, not the motion energy of the weightlifter. But this is the initial kinetic energy is 0 here. From here to here, barbells at rest, barbells at rest. We are talking about the network being done by forces that act on the barbell. And we're talking about the change in the kinetic energy of the barbell. We're not talking about the person's arms or elbows, their head. We're not talking about a bird in the room or the clock on the wall. There's nothing else that we're talking about. We're talking about the kinetic energy of the barbell from one moment in time or place to another moment in time or place. Okay, so the force on the barbell by the person is really complicated. And the barbell takes a very complicated trip in terms of the velocity of the barbell as a function of time. Sometimes the barbell was headed downwards, so the barbell goes up and then rests on the shoulders and then goes up again. So the velocity in time, really complicated. So the strength, or the really interesting thing about thinking with the work and the kinetic energy theorem is we don't really think in terms of the complications that are happening mid-trip. There's lots and lots of moments in time, and there's complicated forces being larger or smaller, changing direction. The velocity of the barbell's got all kinds of complication. But what's really nice about this is that we don't need to know about any of the details in between. We just need to know, what does it look like now? And then what does it look like now? And we can say something about the forces involved. Yeah. So the barbell force is really complicated. But the force the person's force on the barbell is complicated. But the force on the barbell because of gravity, I'm going to shorthand it and just say that it is by gravity. So this is the weight force. The interesting thing is the weight force of the barbell, or on the barbell, is always constant. And this person, right, is acting on the barbell with some complicated force during the trip. But the weight force on the barbell is always really steady. It's just mg, like this, where m is the mass of the barbell. Let's say that the barbell, we're marking the position of the barbell by, say, keeping track of the center of it. So here's the center, here's the center. So what the center has done is moved from its old location right here, this is where the barbell used to be, up to there. So this arrow is the displacement. In this case, I'll just call it a delta y because it's in the up-down direction. So delta y is this displacement arrow that tells me where it used to be and where it is after the trip. It is an arrow that points upwards and has a certain distance. For people, this could be like, say, 1 meter or 1.5 meters, depending on how tall the Olympic athlete is. By the way, short Olympic athletes tend to win these competitions. If you're short and you're really strong, the idea is if you don't need to move the weight through as high of a distance, you're going to not have to do as much work. Yeah. Anyways, so the weight of the barbell is a constant because gravity, regardless of how the barbell's moving or even where it's at, that's always the same. And so thinking in terms of this example, check this out. I wonder what, if anything, can I say anything about how much work the person does? And the answer is yes, but it's not by looking at the person's force. It's actually by looking at something that's very steady and constant. So the point is the work done by the net force is equal to the change in the kinetic energy of the barbell, and the barbell's kinetic energy did not change. So I know that the kinetic energy at some midpoints in time, at all the midpoints maybe, the kinetic energy was something different from zero. But the point is in this situation, the barbell's at rest, and this situation, the barbell's at rest. So this is zero. The work done by the net force, there are only ever two forces on the barbell. On the barbell, if I draw the free body force diagram for the barbell, sometimes there is an upwards big force on the barbell, and an associated with the barbell is the weight of the barbell. Sometimes the force can be smaller than the weight. Sometimes the force applied by the person is really a lot bigger than the weight. Problem is it's really complicated, but the weight force is always the same value. But the point is the force by the person, and this is the force associated with gravity. These two things must have netted up to do no work at all. The work done by the person uses a force that's upwards, and the displacement is always upwards. Upwards and upwards together amount to a work done by the person that's going to be bigger than zero. The work done by the person was effective at lifting the barbell. The person's force was in the same direction as the ultimate displacement of the barbell. So the work by the person is this positive number of joules. But the total amount of work done by the net force is also including the work done by gravity. And the work done by gravity was always pulling downwards. But if the displacement delta y is up, these are anti-parallel. And anti-parallel displacement and force is a negative work done. So that's the negative. And this negative work done by gravity and this positive work done by the person add up to no ultimate work being done. And therefore the barbell can't, from here to here, have gained or lost any kinetic energy. So this is an example of just thinking with the work-energy theorem.